Let's start talking about the global positioning system. It's one of the location sensors that we are going to look at. I would like to start with a question. When we are using GPS in our phones or even in devices such as these GPS devices, what information do we transmit? What kinds of information does our cell phone or this GPS device send out to determine the location of the device? Because when we are using GPS, our ultimate goal is to locate the position of our device, right? So the question is, what information do these devices transmit in order for them to be able to know where they are, what position or what place they are at? The answer, interestingly, is nothing. A device that's using GPS does not transmit anything, transmit anything to the outside world. They don't transmit anything. They only collect, read free GPS signals from GPS satellites and determine their location by calculating information. Now, you may ask, well, if I turn off my data in my cell phone, I cannot check the position of my device, or I can't find my position. Well, that's not so much true, because by principle, the GPS in your phone does not rely on your cellular data. Cellular data, it does not rely on cellular data to make use of the GPS chip in your phone. In other words, if you have maps downloaded in your phone, then even after turning off Wi-Fi and turning off your cellular data, you can still locate yourself, because all cell phones come with this GPS tracking device that is able to freely read this free GPS signals and calculate its position. This is also the reason, if you are traveling for a long time and you are trying to track your position, then it's always very helpful to turn off your cellular data, particularly your cellular data, because your weak signals in cellular data or weak tower signals can drain a lot of battery. So at that time, it is actually very intelligent to turn off your cellular data or even your tower, but then keep the GPS on to save the battery of your cell phone. So in this way, a GPS device or a GPS chip is a passive sensor. It does not transmit anything. It just reads the environment and determines or does what it's supposed to do. A GPS device measures distance to satellites that emit pulse signals. So if we are at Earth and here are our satellites orbiting our Earth, then a GPS device is primarily, what it does is collects information from these satellites, which is free information, and then by calculating these information that it collects, it can measure the distance between itself and these satellites. Now there are 31 satellites in the orbit that transmit signals on multiple frequencies. So we know which satellite we're receiving the signals from, or the GPS device knows that. Now each GPS satellite continuously broadcasts a navigation message. Now this is a message that's free in the air because all satellites are transmitting this message. So this is free in the air. So all of these navigation messages, if you have the GPS device, you can always capture them. And all satellites broadcast at the same two frequencies, 1.6 gigahertz and 1.2 gigahertz. As a reference, the FM radio signals that our radio receives is around 100 megahertz. So GPS signals are at very high frequency. And the message, this navigation message, contains information such as the week number, the time within the week, and so on. Now, what a GPS device that receives these signals must do is demodulate the signal. Demodulate the signal. So, demodulate the message from each satellite for 18 to 30 seconds. That is, it takes some time for it to read these navigation messages. Basically, what it has to do is read the first message, let's say message M1 from one satellite, and read another message, message 2 from the same satellite, and calculate how much time it took to receive the first message, or at what time step t it received the message, at what time step t plus 1 it received the second message. And by calculating the difference between these two times, that is, how quickly it received the first message and how quickly it received the second message, it can guess, or it can calculate how far the satellite may be from itself. So if the satellite is very close to if this is my GPS device, if the satellite is very close to the device, then the time difference between message 1 and message 2, delta t, will be very small. So if we have a very small time difference, we can understand that the GPS satellite may be very close to the GPS device. Similarly, if the GPS is very, very far away, then it will take more time for the GPS device to read second message after it has read the first message. So with some formula based on where you are at, we can easily calculate the distance between the GPS device and the satellite from which we are receiving the signal. For a GPS device to work correctly, we need an unobstructed line of sight. So when we say line of sight, what we mean is if there is a plane flying, or if there is something, if you're under a ceiling, or if you're being covered from somewhere, then the demodulation process doesn't work. That is, it is very difficult for you to receive the GPS signal. So line of sight is important for GPS to work. And we need usually at least 4 GPS satellites. That is, your GPS device must be able to receive signals concurrently from at least 4 GPS satellites to get a precise location. Now we will look into the details of why we need 4 GPS satellites, but we need 4 satellites, GPS satellite signals, to calculate precise location. And the process that is used to receive all of these signals from 4 satellites and determine the absolute location on Earth is known as triangulation. So by triangulating these signals, we can obtain absolute location on Earth. And GPS, calculations of location are usually within a few meters of accuracy. But now if you have a cellular network on top of GPS, so GPS plus cellular network, then your signals can become much more accurate. But now we are talking about only the GPS. So for this reason, GPS signals don't work very well indoors, unlike cell phone towers or cell phone signals. Also, GPS doesn't work very well underwater, and one of the primary reasons for that is the GPS signals are very weak. They are only 10 to 20 decibels, and because they are transmitted at higher frequencies, so 1.6 gigahertz and 1.2 gigahertz, these frequencies are worse for propagation. So anyone bouncing off of wall or ceiling or floor makes the signals very much weaker, so that we are unable to use GPS indoors. Now let's talk about why the GPS, Global Positioning System, requires 4 satellites. Now the reason why we need 4 satellites, because data from one satellite can put you in a sphere, and we need 4 spheres, overlapping spheres, to get a precise 1 x, y, z position. By computing the intersections of these 4 spheres, we can narrow the possibilities into a single point. So now let's look into the details of this. Say, for example, I'm sitting at some random position in Earth, random place in Earth. So this is me, right? And let's say there's a satellite somewhere, and I'm receiving the signals from the satellite. And let's say I can calculate the approximate distance d between me and this satellite, right? So it is possible that if I am anywhere around the sphere of this satellite, I could get the same distance. So even though this is a 2D circle, imagine this to be a 3D sphere, right? A sphere. Then because I know the distance between me and this satellite, I could be anywhere on the sphere of this satellite. So this is my satellite. Now that means my position can be anywhere on this sphere. If I have two satellites, that is, if I have distance d1 with this satellite, and let's say another satellite, and if I know my distance to this satellite, let's say if it's d2, then what I have is, again, I can say that I'm somewhere in the sphere of this second satellite, S2. In other words, if this was all the possible places I could be, so this is the sphere of the first satellite, sphere S1, I could be any place on this sphere. If I know the distance with the second sphere, S2, then the possibilities narrow down to a circle. So the question is, when two spheres overlap, what is the common region or common area? It's a circle. So I could be anywhere on the circle of these two overlapping spheres. Now, if I have the distance d3 with another satellite, then the situation I have is there are three spheres that overlap with each other. So here's my sphere 1, here's my sphere 2, and here's my sphere 3. So if you superimpose three spheres, then the possible places where all of these three spheres will interact are 2, 1 and 2. So if you have three satellites, there are two possible points where you could be at. Now this could be anywhere in the universe, right? So given three satellites, we can narrow down your x, y, and z position anywhere in the universe to two possible values, maybe 1 or the second value 2. So adding one more sphere to this chooses or helps us choose between one of the two possible points, narrowing down to a precise position. So the last satellite, the fourth satellite, gives you the exact location. Now we can't be anywhere in the XYZ of the universe, right? We are always at the surface of the earth, approximately always at the surface of the earth. So for that reason, if we already know the altitude, that is how up or how down we are from the core of the earth, then we usually don't need the fourth satellite. So say for example, when we are driving, we usually know that we are at the ground level, so the last intersection is not needed. However, if you are flying, then the plane could be anywhere. So for when you are flying, you definitely need, for example, in a plane, you definitely need the information from all four satellites. So here's a summary. If we are at Earth, satellite 1 gives you a single sphere. Satellite 1 and satellite 2 give you a circle, intersecting circle where we could be. And satellite 1, 2, and 3 together give us two possible points. And then adding satellite 4 gives us one specific point where we could be in the 3D space.